today our target is to learn about the Carnot heat engine. So Carnot heat engine, before dealing this Carnot heat engine, we need to know the small concept. Very one more question, small concept is the Joule's law. Joule's law. So Joule's law, it will tells that the conversion of the mechanical work into heat energy. So that means it will, these law will tells that the conversion of mechanical work to heat energy. So it tells that how it will conversion means, so the mechanical work W is directly proportional to the heat energy. So this is the Joule's law. That means what is it is telling? That means the definition of Joule's law means the amount of mechanical work, MW means mechanical work. So mechanical work done on the system is directly proportional to the amount of heat produced in the system. The amount of heat produced in the system. So this is the Joule's law will tells that. So that means the amount of mechanical work done on the system is directly proportional to the amount of heat produced in the system. That means if you are doing the work on the system means definitely certain amount of heat will be produced in the system, that both will be directly proportional. So the W is directly proportional to H. While you removing this one, J1 proportionality constant is there. This will be named as the mechanical equivalent. This proportionality is named as the mechanical equivalent. Here J is the mechanical equivalent. This will named as the mechanical equivalent. So how can we define this J value? Means J is equal to, I am sending H this side, W by H. So if you take H as the unity, so H is equal to unit, that is equal to, it is nothing but unit amount of heat energy. So how can we define? Means when H is equal to unit amount of heat energy, then J is equal to W. How can we define mechanical equivalent? So it is nothing but the mechanical equivalent is work done on the system to increase the unit amount of heat energy in the system. So how can we define? Means the amount of work done on the system, work done on the system, for which purpose we are doing work on the system? To produce unit amount of heat energy in the system. To produce unit amount of heat energy in the system. Is called mechanical equivalent. Is called J. This is the value. Now if we take the units for J, means units for J is equal to W by H. W is equal to work. Work is in the terms of joules. H is the heat. Heat is in the terms of calorie. So then joule per calorie. Joule per calorie is the SI system unit, and in serious units means erg per calorie. This is the CGS system units. Now you know that one joule is equal to how many? No. Heat energy, not temperature. Temperature is the Kelvin. Heat energy. Heat energy is the calories. Heat. Heat energy. So then. Now, if we already know this one, 1 joule is equal to 10 to the power of 7 eggs. So to this constant value, what is this constant value? J constant value is equal to 4.186 joule per calories, or near value we can take means 4.2 joule per calorie in the SI system, or if you take the CGS system means 4.2 into 10 to the power of 7 egg per calories. This value we need to know. This is the very important formula. We are going to use this formula while we are solving the problem. They will use the amount of work done. They may ask how much amount of heat energy will produce. Like that they will ask this question. Now let me recall the small concepts. So in the cyclic process, what is the efficiency of the one cycle? What is the efficiency of the one cycle? Neta is equal to work done total divided by amount of absorption, heat energy absorption. Absorption, we have the formula. Another one, we have the formula Q of absorption minus Q of released, divided by Q of absorption, we have the formula. Other formula also we have 1 minus Q of released divided by Q of absorption, we have the formula. So one more formula I am going to recall from you. So we know the formula for the adiabatic process. What is the adiabatic work done in the adiabatic process? Tell me, will you please give the information? What is the work done in the adiabatic process? Work done in the adiabatic process. W is equal to P1 V1 minus P2 V2 divided by gamma minus 1. This formula. Otherwise, we will take that nRT divided by gamma minus, nR divided by gamma minus 1 into T1 minus T2. T1 minus T2. This is the formula we are having. This is the work done in the adiabatic process. Work done in adiabatic process. So these are these formulas you need to know before dealing this one. So what is the work done in the isothermal process? Tell me the formula for work done. Work done in the isothermal process. Isothermal process. Tell me the formula. So the work done isothermal process W is equal to, tell me, W is equal to
V2 by V1.
RT into log of nRT into log of E2 by V1. V1. This is the formula.
nRT into log of V1 by V2.
Okay. Otherwise, we will take the no. You are telling one more formula, na?
Yes, sir. P initial by P final.
P final. Okay. NR into P initial. Log of V final minus V initial. Okay, na?
P, sir.
T initial minus T. Okay. No issue. Let me. This is the enough for us. So let me keep this one. We will continue that one next one. No issue. So now we are going to the Carnot heat engine. Carnot heat engine. Very important. Carnot engine. Very important. In the generally they will ask in essay type questions, 10 marks question they will ask this one. Generally they will ask the 10 marks question. So very important. Now before what does mean by Carnot engine means? It is a heat engine only. But but this heat engine is the ideal case heat engine. It is a heat engine. It is working. It is a ideal heat engine. It is a ideal engine. So because ideal engine means this engine will give the maximum efficiency only. Other than heat engine, this engine, no engine is not available. So it is a theoretical heat engine. It is a theoretical engine. That means in the practical this engine cannot be constructed. So just only on the theoretical self only we will have him. So in practical this engine cannot be exist. So that is you need to remember. So what does mean by Carnot heat engine means a engine. It is a cyclic heat engine. How can we define a Carnot heat engine means? Let me give the definition for the Carnot heat engine. Very small definition only. Let me give that one. Very small definition. So what does mean by a Carnot heat engine means? It is a reversible heat engine. It is a reversible heat engine. So which is operating between BW means between two temperatures. One is at high temperature T1, and other is at low temperature T2. This is the definition for the Carnot heat engine. So it is a reversible heat engine which is operating between two temperatures. One is at high temperature T1 and other one is the low temperature T2. So in this heat engine, what are the parts which is having the heat engine means the parts in the Carnot heat engine means parts in Carnot heat engine. In the parts, what are the parts? They have the Carnot heat engine means there are main four parts are there. First one is the source. It will consisting of source. Source is nothing but it is a high temperature area. It is a high temperature area. So that means these place will having the high temperature area. So these high temperature area generally they will take the T1. The temperature of the source generally they will take the T1. It is a high thermal efficiency part. It is a infinite thermal efficiency part. So what does mean infinite thermal efficiency part means? If you are taking some amount of heat energy from the source means the source temperature should not be dropped down. So that means if we taken out some part of some energy from the source, the temperature of source should not decreases. Source will not be decreases. So that is a very important because of the source is the thermal efficiency is infinite. Infinite means to decrease the temperature of the source, we need to drag the infinite amount of heat energy. So that means we are taking the finite amount of heat energy. In that case, the temperature of the source may not be decreases. It will same temperature. That means the source temperature is always constant. The source temperature will always constant. Constant at T1 temperature only. Even we are taking the heat energy from the source means the temperature will not be dropped down. So the second one is the sink. Sink also same properties only, but it is the low temperature area. So all properties are same, but it is the low temperature area. It is a low temperature part. Remaining two cases are same only. So it is the thermal efficiency of the sink also. It is the infinite thermal efficiency. That means thermal coefficient of this one, it is the infinite. That means to drop down, to rise the temperature of the sink, we need to supply infinite amount of heat energy. That means if we supply the heat energy to the sink, some energy of heat energy if we supply to the sink means it won't decrease its temperature. That means the thermal coefficient of sink is infinite. That is if we supply some amount of heat energy to the sink, the temperature will not be rises. The temperature will not be changes. That is very, very important. What does it mean? What is the coefficient of thermal efficiency means? What is the thermal coefficient? Thermal coefficient means to rise the temperature, how much amount of heat energy is needed. That is important of coefficient of thermal efficiency. So the coefficient of thermal efficiency is infinite means to rise the 1 degree temperature, we need to supply the very large amount of heat energy. That is the infinite amount of heat energy we need to supply. But finite amount of heat energy. With the finite amount of heat energy, the sink temperature will not be changes. That is the very, very important. Now, in the same similar manner, that will consisting of working substance. So working substance, generally in the Carnot heat engine we will take the ideal gas. In the Carnot heat engine. They will consisting of ideal gas. So that means when we are using this ideal gas means we will apply the ideal gas equations in this system. While we are using this one, we will apply the ideal gas equations. Now to hold this ideal gas we need to use the cylinders. So we need to use the cylinders which can be consisting of working substance and cylinder. So cylinder means one type of chamber it will consisting of. So these cylinder will what is the property of cylinder means it can hold the working substance and also it will hold the working substance and also it will consisting of movable piston. So it consists of movable piston. So piston it will consist. So that means while if the expansion is appear, the piston will move back. If the compression is appear, the piston will drag to inside to the chamber. That is very, very important. And also the walls of this cylinder is thermal conducting walls. That means the walls of cylinder is a thermally conducting walls. Thermal conducting walls. That means what is the meaning of this word? So that means these walls can allow heat energy from the surrounding to the system. They can allow heat energy from the system to surroundings. These walls are allowing the heat energy from the system to surrounding and surrounding to system. That we will having the this is the thermally conducting walls. Now if we take another part, insulating cap. Insulating cap. Insulating cap means if we want to block the flow of heat energy from the surrounding to system or system to surrounding, then one insulating cap will be used. That means like this shape it will having. What is the property of insulating cap means these walls are insulating. It can block. So it will use for to block flow of heat energy from where to where we are blocking flow of heat energy from system to surroundings, vice versa. That means from surrounding to system. That means this is the insulating cap. Means in this one we kept the cylinder. Means this cylinder should not allow. They won't allow to enter the heat energy from the surrounding to system. It will block. Here. Otherwise, heat energy is moving from system to surrounding. Means it will block here. So that means it won't allow to pass the heat energy from the system to surrounding as well as the surrounding to system. That is a very, very important of the insulating cap. Where we needed, we can use this insulating cap and other one. So in the Carnot heat engine, what are the steps? What are the process it will involve? Means in the Carnot heat engine, it will consist of four following stages. So that means it will consist four following stages. So that means in orderly they will follow these stages. What are those? Means the first one, isothermal expansion. It will do isothermal expansion will happen. The second stage will adiabatic expansion. Adiabatic expansion will take place. The third one, isothermal compression. Compression will happen. Isothermal compression will happen. The fourth one, adiabatic compression will happen. Adiabatic compression will happen. These are the stages in orderly the Carnot heat engine will be involved to complete the cycle of the one cycle. As it is a reversible process now, so it will bring this initial state while by completion of these many stages from initial state to final state. How it look like means so let me start this. This is the graphical representation of the Carnot heat engine process, taking the pressure in the y-axis and volume in the x-axis. Now let me state at the initial state that the system is up to here. The system is here. So the position of the system is I am taking the P1, pressure of the P1 and volume is the V1 and the temperature of the system is the T1. Let's assume like this. So the initial, the first stage Carnot heat engine is involving isothermal expansion. Isothermal means so the system should allow the system should maintain at a constant temperature. The system must be maintained at a constant temperature. So the T must be constant. So it is the expansion. It is the expansion means let me take this is the system. So while it is expanding means the system must be done work on the piston. So while the piston is working, system is working on the piston means definitely the energy of the system must be dropped down. That means the temperature of the system will decreases. Are you getting that one? Hello?
Sorry, sir, explain.
One more time. What I am telling that, so it is the expansion process. Expansion means who are expanding here? So the system is doing the work. Expansion means who will push this one? The inside the gas is there. The gas will push the piston. So when the gas is pushing the piston means the gas is done the work on the system. So the gas is done the work on the piston. So that means why if we did the work means definitely our energy will be losers. So here gas is doing the work. While gas is doing the work, definitely the temperature of the gas must be dropped down. Are you getting or not?
Yes, sir.
So, but it is isothermal. Isothermal means in the world the temperature must be constant. That means what will happen means to keep the system at constant temperature, maintain at constant temperature means what we do means first of all we will connect this cylinder to the source. So we will connect this one to the source means here we kept the source. The temperature of the source is at highest temperature T1. While it is dropping this temperature, some of the heat energy will allow to pass from source to system. That some of the heat energy will allow to pass the source to system. That heat energy, let me take it as a Q1. Because we need to maintain the constant temperature. Here is the source temperature T1 is there. Even it is expanding, even it is doing the work on the piston, so it won't drop down. It is taking the energy from the source. It is absorbing the energy from the source. It will maintain the same temperature. But it is expanding means the piston will move somewhat another position. Definitely the pressure will changes, volume will changes, but the temperature must be constant. Are you getting or not?
Yes, sir.
So if it is increasing means volume will be changes. So the volume is increasing means so if volume is we are here. So this is the volume position here. It is expansion means definitely the volume will be somewhere, some another part it will go. So other than this one, in right side it will move. But while it is moving, the pressure must be dropped down. It is the pressure position here means pressure must be dropped down. Somewhere it will come to this position. That means it is coming to this position like this. Slowly it will decrease us. It is the expansion position. It will come to up to here. So that means what I am taking this position. What are the system thermodynamics parameters? It is the new parameter P2 and new volume is V2, but the temperature is at the same position T1. Are you getting that? It is the isothermal expansion. So to do this one, system is absorbed for some heat energy Q1 is absorbed. Are you getting or not? Q1 heat energy is absorbed from the source. From the source, this energy is absorbed. Now this process is completed. Now we are moving. Let me start from A. Now we move to the B point. Now what is the steps we need to move? So we need to do the adiabatic expansion. Adiabatic means we need to do the this process at a constant thermal energy. That means in the constant thermal energy means we should not allow the heat energy from the surrounding to system. Are you getting or not? Hello?
Yes, sir.
So that means to block the flow of heat energy from the surrounding to system means this case what we need to do, the cylinder must be covered with the insulating part. This is the insulating part. We covered this piston and cylinder with the insulating part. Now we are allowing to expand this gas. We are allowed to expand this gas means the system is doing the work on the piston. It is expanded to another position. While it is expanding, some of the energy must be utilized to expand this one. While it is work is done on the piston means definitely the temperature of this system must be dropped down. Are you getting or not? It is, so it is the expansion. Here is the expansion is there. It is the expansion means expansion. What is the word? The gas is doing the work on the piston. So while it is pushing the piston means definitely it will use its internal energy to push the piston. So while it is doing the work on the piston, definitely the temperature will drop down. So the temperature will fall down. It will move to the another temperature T2. Let's we take the temperature is the T2. Are you getting or not? Hello. So that means adiabatic. Adiabatic means the temperature must be adiabatic means the thermal energy must be constant. So there is nothing heat energy is there here. Nothing heat energy is there. So no change of heat energy in this one. Internal the temperature only drop down. The total amount of heat energy is at constant energy. Constant only. Now the temperature is dropped down. Now it is the expansion. So in adiabatic process, the graph will be slope will be very less. In isothermal process, graph will be slope will be very high. That's why I am drawing with high slope graph like this. Another pressure and another volume and another temperature will come. So another pressure P3, another volume V3, but another temperature we taking the T2. Another temperature we taking the T2. So it is the isothermal expansion. There is no any heat flow from this one. That's why I am not indicating any Q value here. Now what is the next process means here is the isothermal compression. Isothermal compression means at the same temperature we need to compress this piston. So we need to compress means we need to work on the external work is need to done on the system. How to do at the same temperature only? Let me do this one. So it is the piston, it is the somewhere another position is there here, another volume is there. To compress this means we need to do the work on the system. We need to do the work on the system. If we are doing the work means we are supplying the indirectly we are supplying the heat energy to the system. Hello, are you getting or not?
Yes, sir.
So if we supply the heat energy, definitely the temperature will rise. The temperature will rise in the system, but these process is the isothermal process. Isothermal process means that the temperature must be kept at constant. In the previous case, what is the temperature? T2. To hold the temperature at T2 means we need to connect these cylinder to the constant temperature of the sink. Here is the constant temperature of the sink T2 is there. We are connected this cylinder to the sink. That means if the temperature is rises, that means this energy, what is the energy that supplied to the system? This energy will release to the sink. This energy to release the sink, it will maintain at the same constant temperature of the previous stage. That same temperature only will hold this one. Are you getting or not? Hello? One more time I am repeating here. So please remember here, what is this one? It is the isothermal compression. Compression means what does it mean? So we need to push the piston towards to the to decrease the volume. While we are pushing this one, we will indirectly we are supplying the sum of energy to the system. If we are supplying the heat energy, definitely the temperature will rise. To hold this one, to what we given the energy to the system, to hold this at the same constant temperature means at the same constant temperature what is there in the previous case T2, that same temperature of the sink is connected to the system. That means it is connected to the system means the sink is a low temperature. How much amount of heat energy, how much amount of energy is supplied to the system, that energy is comes out. That energy is comes out from the system to sink. Because of these walls are thermally conducting walls. The same that energy is comes out. That means the Q2, let's assume we don't know that one. Q2 we are taking, Q2 amount of heat energy is ejected, is released from the system. Now it is the compression. Compression means definitely the volume, the final volume must be changes to, it will go back to going back to the lower value of the V. So that's why I am taking back this one like this direction, we push this one. So it is going back like this, it is going, but all values, but it is isothermal compression. The temperature must be kept at constant. T2 state, here also T2 is there, but volume and pressure will changes. So P4 and P4 and V4 we will achieve. Are you getting or not? Hello? But what is happened here? In this one, Q2 amount of heat is released from the system. Released from the system. So Q2 amount of heat energy is released from the system. Now what is the another state? Adiabatic compression. Adiabatic compression means in this one we are compressing. So while we are compressing here, let me take somewhere here, we are compressing this system. But what is we are doing? We are not allowing to flow the heat energy from the surrounding to system while we are compressing. So what we need to do? We need to cover this total cylinder with insulating walls, because of we are not allowing to flow of heat energy from the surrounding to system or system to surrounding. So what we are doing? We are compressing this system to increase the temperature from T2 to T1. T2 to T1 we are increasing, and we are bringing the system from initial state of P1 to V1. While we are compressing this one, we bring back to the system from where we are bringing P1 to P4, V4 to, we bring back this one up to P1 to T1. This is the adiabatic compression. This is the adiabatic compression. It is a one cyclic process. In this cyclic process, there are 4 stages are there. This is the first stage, A to B. This is the second stage, B to C. This is the third stage, C to D. This is the fourth stage, D to A. Like this we are moving. Now let me take one by one stages, each and every stages. We need to know the what is happening, what is the work done, what is the work done in each stage. Let me take the first stage. In the first stage is nothing but from A to B we are moving. That is nothing but adiabatic compression. Sorry, isothermal compression. Expansion. Isothermal expansion. So isothermal expansion means we know the formula for the isothermal expansion. What is the work done? Work done in the isothermal expansion, W is equal to nRT into log of V final value minus V initial value. This is the standardized formula we are using. But in our case, from which state to which state is it moving? So the initial stage is this one. This is the final stage. Let me take the what is the initial stages and final stage. It is the initial stage. Initial stage 2. It is moving final stage. The initial stage, what is the thermodynamic parameters? These are the P1, V1, T1 is the thermodynamic parameters here. What is the final stage parameters? P2, V2, but T1. That is the very important. So this is the isothermal compression. So that means the first stage work done I am denoting with the W1. W1 is equal to nR. In this stage the temperature is the T1. Log of final volume is the V2. The initial volume is the V1. This is the formula for the first. Let me take this the equation number 1. Now, while we are moving to the second stage, what is the second stage? Second stage is nothing but adiabatic expansion. Expansion is there. So in the adiabatic expansion, where we are moving from B to C, we are moving. So adiabatic expansion general formula, let me tell you the general formula. Adiabatic expansion work done is equal to nR divided by gamma minus 1 into bracket open T1 minus T2. T1 minus T2 means nR divided by gamma minus 1 into T initial value minus T final value. This is the formula we are having. Are you getting or not? Hello?
Yes, sir.
So then let's take this B to C. What are the initial condition? What are the final condition? Check this one. This is the initial condition P2, V2, T1. The final conditions are P3, V3, T2. So let me take this one. The initial conditions are here. Initial conditions to final it is moving. The initial conditions are P2, V2, T1. The another conditions are P3, V3, T2. These are the values. Now this one, what are the work done? Let me take denoted with this is the second stage na. W2 I am taking. That is equal to now I am taking NR divided by gamma minus 1 into final initial temperature minus final temperature. Initial temperature is the T1 minus final temperature is the T2. So, but one thing you need to remember here, in these two processes, the system is doing work. That's why these are the positive words. These are the positives. Because of the system is doing the work. Are you getting or not? So the system only doing the work. That's why we will consider as a positive one. So now we will go to the another one. Now the third stage. We will move to the third stage. Third stage means it is the isothermal compression. Okay, na? Isothermal compression. So where we are moving? We are moving from C to D. We are moving from C to D. So C to D means isothermal compression. What is the work done formula? So even it is the compression or expansion, the work done formula W is equal to it is the isothermal na? Isothermal compression W is equal to nRT into log of V final value minus V initial value. This formula only. But now no issue. Let me take this one. It is the isothermal compression. Now what is the initial state here? What are the initial stage? What are the final stage here? So here is the P3, V3, T2. So we are moving from P4, V4, T2 only we are moving. Now that in the third stage, now W3 is equal to NR T2. In this one temperature is the T2 log of final volume is equal to so V4 divided by initial volume is equal to V3. But one thing you need to remember, this stage work is doing on the system. Are getting or not? In this stage work is done on the system. That means we need to take it as the negative. So W3 is the negative. That's why W3 is equal to minus nRT2 into log of V4 by V3. That is the very, very important. Are you getting or not? Hello? So done. Now we are moving to the fourth stage. So in the fourth stage, what is this one? That is the adiabatic compression. So adiabatic compression. Adiabatic compression means from where to where we are moving? C to D we are moving. So adiabatic compression formula already we know in the we know. So what is the initial stage? What is the initial stage? What is the final stage? Initial stage is equal to P4, V4, T2. The final stage is equal to P1, V1 and T1. We achieve like this. But in the adiabatic compression, what is the formula, work done formula? W4 we take. W4 is equal to NR divided by gamma minus 1 into T initial value. T initial value is equal to T2 minus T1 final value is equal to T1. Hello? Is this only, na?
Yes, sir.
So, but one thing you need to take care about here. But is there correct only we did? T initial value minus T final value. Let me check the formula here.
Yes, sir.
T1 minus T2. T1 minus T2. Let me check one second, please, 1 second. I confused little bit. Let me check. If it is a very, very important question, If I did some mistake means total bill goes to wrong. So let me correct in the starting stage only. Yes, we are correct only. We are performing everything correct only. Now yes. Now here, but one thing you need to concentrate here. These values must be. If we take these values. Yes, initial stage and final stage. But in this case, work is doing on the system. On the system means W4 is the negative value. So W4 is the negative value means W4 is equal to NR divided by gamma minus 1 into negative term of T2 minus T1 we will get. But one thing you need to take care about this one. Okay. If we add these two means T2 minus T1. What about? Will you please look on this one? Whether W1 and W2 both are same or they are different. Fourth stage, they are same or they are different. Hello, are you there or not? Hello.
Yes, sir.
Okay, done. Let me check once again. So what are the W1, W2? Will you please check that one? W2 is equal to what the values we are getting? W2 is equal to NR into T1 minus T2 divided by gamma minus 1 we got. W4 is equal to what we get? What we get means
By gamma minus 1.
okay, we got like this NR into T2 minus T1 but negative
Negative sign.
no, don't use this negative sign. So as we are following the conversion, as we are following the T1 and T2 temperature or initial stage and final stage we are using, don't use this negative sign. As we are following initial and final stage conditions, conditions, no need to take negative sign. So without taking the negative sign means here also I need to change here negative sign, no need to check, because of we are following the initial and final stage conditions we are following. That's why no need to take negative sign here. But we need to remember work is doing on the system. That is very enough for you. So now divided by nRT divided by gamma minus 1. Now will you please look on this one? So these values are both are same. In one case work is doing on the system. Work is doing by the system. This is the work is doing by the system. Just arrow I am indicating work is doing by the system. So in this case work is doing on the system. If we add these two, what will happen? Let me check this one. W2 plus W4 is equal to, just I am adding this one, NR into T1 minus T2 divided by gamma minus 1 plus I am taking the negative sign here. Here means I am keeping this negative sign here. I will write just interchanging the position of this one, T1 minus T2. That negative sign I am writing here, NR divided by gamma minus 1 into T1 minus T2. Will you please look on this one? These two values are same only, but one is in the positive, another one is the negative. Then these two will be cancelled to each other. We will get the zero value. Now we will please look on this above formula. So the total work done W is equal to W total is equal to, we will add the W1 plus W2 plus W3 plus W4, we will add like this. W1 value, anybody will please tell me the W1 value? W1 value. NR T1 log of V2 by divided by V1 plus these two values are going to 0, no need to write once again, plus log of NR T2 into log of will you please anybody? V4 divided by V4 divided by V3 na?
Yes, sir.
V4 divided by V3. Now will you please look on this one? If you look on this one, it is the total work done. It is the total work done formula. So now I am interchanging this formula. So just I am interchanging for simplicity only to easy solve this one. NR T1 log of V2 divided by V1 minus NR T2 into log of V3 divided by V4. Because of we know the formula, log of A by B is equal to minus log of B by A. Just interchange this position. This position is sent to so numerator. This position is sent to denominator. That while you need to change this one, we need to get that in. So we have the formula log of A by B is equal to minus of log of B by A. Log of B by A. This formula I used, just I interchange this one, total work done. This is the total work done. So the total work done value this one, but we need to know the what is the efficiency. What is the efficiency of the Carnot cycle? This only they will ask efficiency of the Carnot cycle. Carnot cycle. Carnot cycle means Carnot cycle efficiency means how much, what is the formula for efficiency of the Carnot cycle? So any reversible process efficiency neta is equal to, we have the two formulas, the total work done divided by Q amount of energy is absorbed. This is the formula we are having. Another formula also we are having, Q of absorption energy minus Q amount of released energy divided by Q of amount of released energy divided by Q of amount of absorbed energy. This formula we have the formula. So will you please look on this one, neta is equal to Q total is equal to we have the formula, just now we find out NR T1 into log of V2 by V1 minus NR T2 into log of V3 by V1, we have the formula. Now tell me anybody, anyone you are running the notes means please repeat this one. I will write here. Tell me NR T1 into log of V2 by V1 minus NR T2 into log of, what is the value here? Here is the V3 by V4, I hope. V3 by V4 divided by Q absorption. Q absorption, what is the value? Q absorption, and Q absorption is nothing but work done in the first process na, work done in the first stage na. So Q absorption is nothing but work done in the first stage. So let me take this value na. This value is nothing but work done in the first stage. So but one thing you need to take care. So W1 is equal to NR T1 into log of V2 by V1. This formula is there. Now take that one. Now take this one. But let me write this one. So here NR T1 into log of V2 by V1. But somebody they may ask the question. So how can we take W is equal to Q1? These may not be equal, na? You already told W is equal to JQ. You told that W is equal to JQ. You told that. So for simplicity, let me take J is equal to unit. From this case, as Carnot heat engine we are working, let me for simplicity. So otherwise we will come to we will use this one. We need to convert this value also here. Here also we will convert the heat energy. Here also we need to convert the heat energy. From that case also we will convert. Otherwise, to do this one, somebody they may have the doubt also. Let me continue. Are you getting or not? Why so the students, more intelligent students, they may ask the question like this. Here you used the Q, I used here is the Q, Q1 value, W1 value I used, but I am telling that is the Q1 value. How can I prove means? But W and J relation is, W and Q relation is W is equal to JQ. But I am not using the Q1. So for this purpose only, please keep this J is equal to 1. Otherwise, we need to do this one also, W1 and W1 also. In this case also W will get. How it will become means, let me do one small process also here also. Let me do here. So here W1 is there. I need to convert this one. How it look like? Please do this one. How we are going to convert? Please concentrate here. So what is we are having the what is the efficiency formula? Efficiency formula is equal to Q1 minus Q2 divided by Q1. It is the formula. It is the heat absorbed. It is the heat released. It is the heat absorbed. This is the efficiency formula neta. But we are having the W1 values. We have the W3 values. We have only W1, W3 values set. From this W1 we need to get the Q1. From this W3 we need to get the Q2 values. Are you getting or not? Hello? See this one. See the diagram.
Yes, sir.
Will you please see the diagram? What is there? Will you please look on this diagram here? So here we are doing the work. We calculated the W1 in this process. We said that the Q1 amount of heat energy is absorbed in this one. We calculate the W3 in this process, but we said that Q2 amount of heat is released in this process. But we did not have the relation in between the Q1 and W1 and W1 to Q1 and W3 to Q2. We don't know that relation. We need to attach that relation also. So let me get the relation also here. So here, we have the formula for Q1 is equal to what is the formula? We know that W is equal to J into HRQ. J into Q is there. Then Q is equal to W by J is there. This formula we know. So in the initial state I told Joule's law. Hello. So Joule's law. How much amount of work is done on the system is equal to the same amount of heat will be released from the system with multiplication of J. So Q is equal to W by J is there. Now for this one, for simplicity, I am taking 1 by J is equal to small a. That is equal to Q is equal to A into W. This relation is there here. Q is equal to A into W. So let it be 1 by J is equal to Q into W. So from this one, Q1 is equal to, tell me the formula. Q1 is equal to from the W1, tell me, A into NR into
NR T1 log of V2.
NR T1 into log of V2 by V1. This is the formula. Tell me this one, Q2 formula. Q2 is equal to A into NR T2 into log of V3 by V4. V3 by V4. Now you don't have any doubt now how we get the A value. A value is nothing but 1 by J. We taken from A value 1 by J. So then can I use this one Q1 Q2 directly? So now the formula is neta is equal to Q1 minus Q2 divided by Q1. Then substitute these values on A into NR into T2 into log of V2 by V1 minus V2 by V1 into A into NR so I written 2 times nr. So nr into T2 into log of V3 by V4 divided by V3 by V4 divided by now Q1 value. Q1 value. Please tell me Q1 value. So Q1 value is equal to this only, na? A into nr into log of V2 divided by V1. This is the value. So in this one, the common terms are ANR, ANR, ANR are the common term. That means we have the formula T1 into log of V2 by V1 minus log of V3 by V4 divided by log of V2 by V1. This formula we achieved for the neta value. But we need to simplify this formula one more step. How can we simplify? Means let me draw once again this diagram. We are moving like this. After that we move like this. After that we move like this. After that we move like this. So these are the process we are having. From A to B we moved. From B to C we moved. And C to D we moved. Just I am taking this portion. This portion is the adiabatic. This portion is the adiabatic expansion. Are you getting or not? This is the adiabatic expansion. Here is the P1 V1 T1 is there. Here is the P2 V2 T1 is there. Here is the P3 V3 T2 is there. Here is the P4 V4 T4 is there. So after that we move to the P1 V1 T1. So in this process we are applying B to C. We are moving. B to C is the adiabatic compression. Adiabatic compression. So adiabatic compression means which formula will holds good. So in the adiabatic compression, PV power gamma will holds the good. So this formula will be constant. This formula must be holds good. That means P1 V1 power gamma is equal to P2 V2 power gamma is there. But will you please look on this one? We need to get the relation V terms. V terms we need to get the relation. But I am concentrating in the T terms also this formula. Will you please recall the T terms of this formula? T and V terms. T and V terms. In terms of T and V terms. Anybody will you please give the relation of the T and V terms of the adiabatic expansion. T and V terms means TV power gamma minus 1. TV power gamma minus 1 is equal to constant. Hello.
B to C adiabatic expansion.
Okay, expansion. Sorry. It is the expansion. So in adiabatic expansion, in the T and V terms, TV power gamma minus 1 is equal to constant. Then T1 V1 power gamma minus 1 is equal to T2 V2 power gamma minus 1. But we are taking it the initial state. This is the for your easy understand. I am taking this one. T initial of V initial of gamma minus 1 is equal to T final of V final of gamma minus 1. This formula we are using. We are using this formula. Now will you please look on this one? What is the initial values here? We are moving V2 T1 to we are moving V3 T2. V3 T2 we are moving B to C na V2 T1. So from B to C where we are moving means V2 T1 to V3 T2. So use this formula here. We use this formula here. Please use this formula. So this formula please now tell me this formula that is equal to T1 V2 gamma minus 1 is equal to this formula I am using. So that is equal to T2 V3 gamma minus 1. This formula we use. So let me take only T1 power T2. T1 by T2 is equal to V3 by V2 whole to the power of gamma minus 1. Gamma minus 1 we achieve. So in the similar, let me take this is the Roman number equation number 1. So in the similar manner, check this one adiabatic process where it is another adiabatic process here is there. So we are moving from D to A. D to A we are taking this one. D to A also adiabatic process only. In this process also we will apply this formula from which what is the parameters? Initial thermodynamic parameters. What are those? Tell me initial thermodynamic parameters. So P4, V4, T4 we are moving. P1, V1, T1 we are achieving. So initially we are here. Finally we achieve up to here. Huh?
P4, V4, T2 solution.
P4, V4, T4 is the initial. So we move to P4, V4, P4, V4, T4, so T2, T2, I written here wrong, T2. So that means from here we are moving, so initial state to P1, V1 and T1 we achieve. So apply this formula in terms of T initial, V initial, gamma minus 1, T final, V final, gamma minus 1. So it is the initial, it is the final. So that is equal to P4, T2, P4, we need to apply in the V and T. Wait. So T2, V4, gamma minus 1 is equal to T1, V1, gamma minus 1. This is the formula. So again I am taking only T1 by T2 only. So again I am taking T1 by T2 only. So I am sending 2 to this side, this word this side. That is equal to V4 by V1 whole to the power of gamma minus 1. Take it as the Roman number 2. So Roman number 1 and Roman number 2 equation left side values are same. But we can compare the right side values are both must be same. So Roman number 1 from Roman number 1. Equation number 1 and equation number 2 LHS are same. So then RHS must be same. Are you getting or not? Hello?
Yes, sir.
So that means what are the Roman number 1 RHS value? V3 by V2. So RHS values V3 by V2 whole to the power of gamma minus 1 is equal to another formula V4 by V1 whole to the power of gamma minus 1. So both are same powers. We can cancel the powers. So both are same powers. We can cancel the powers. V3 by V2 is equal to V4 by V1. But our problem is here. Yes, 1 minute, ma. Please wait 1 minute. I will come back. Please wait 1 minute. Apply this formula, please. Come in. One minute. So where we stopped, our problem is neta is equal to, let anybody will please tell me the neta value, where neta is equal to, tell me, log of V2 divided by V1 minus log of V3 T1 into log of T2 by D1 into T2 into log of P3 divided by V4 divided by T1 into log of V2 divided by V1. So now our goal is this part is somewhat problem is there. So from this one will you please get the relation V2 by V1 is equal to, now I am sending V1 this side and V3 this side. So V2 by V1, V2 by V1. Otherwise, let me do first one. V1 by V2 is equal to V3 by V4 by V3. Now invert this one. Let me invert this one. So V2 by V1 is equal to V3 by V4. Are you getting or not? V3 by V4 only, na? Hello. So that means it is indirectly saying that log of V2 by V1 is equal to log of V3 by V4. Both are same. Are you getting or not? Hello.
Yes, sir.
So that means these two parts, that means this part and this part are common, that is equal to this value. I am taking the common term from this one. So that means neta is equal to the common term I am taking T1 minus T2 divided by T1. This common term I put it here, log of V2 divided by V1. So I am taking V2 divided by V1 divided by, in the bottom also V2 divided by V1 is there, denominator term also is there. These will cancel. So then neta is equal to T1 minus T2 divided by T1. This is the formula for the formula for the thermal efficiency of the Carnot heat engine in one cycle. Carnot heat engine, one cycle, thermal efficiency. This is the very important formula. So we need to perform some problems to this one. It is the continuation process. That's why I took this much time. Don't feel I took much more time. Is there any issue regarding this? Hello. Let me. No.